This is an optional tool, but one which by the time you're doing all these tools, it's nice to have these type of specialty tools. And I should point out too, by the way, you know, these tools, you're gonna have your hand out, and then you're gonna make them. And then the first thing that you're gonna want to do is you're gonna want to check your tool impression marks and see if they're leaving marks the way that you want. So you want to do that if you don't want to spend a lot of time, you know, running through forging. The best way to use to do it is to use plasticine, and then run through and make sure that your tools are all leaving impressions the way that they need to. If you can make adjustments on the tools that you have, then go and make those adjustments until they're working right. And if you find that you've made one too big or too small, rather than converting that one, if it's possible, you might even just consider just making another one. I do a lot of, you know, 3-dimensional horse heads out of 3/4 inch stock. When I was making my tools, every once in a while I'd make one that was a little small. That just allowed me to make other size and type of heads. So, you know, if you're going along and, for instance, you make like a punch for the eyeball, and you have a little weasel eyeball for your bear, well, now you can make a weasel. So keep the weasel eyeball and make a bear eyeball punch as well. This butcher style fuller is for the eye here, but the slant here would be to the cheek side. So you still have a hard ridge for the eye, for the brow, but then the rest can sort of slope down into the face. Okay, so grinding. I'll do a little bit of grinding. Mostly I'm doing filing. Grinding is obviously going to save you some time. Unless I have the opportunity to do hot work, I generally prefer to do grinding. But when you're doing grinding, consider that this is another tool that you need to be safe around. You should have guards and tool rests. Don't have any loose clothing or hair. A lot of people think that I wear my hair in a man bun as a fashion statement. It's because I don't want it getting stuck in any wheels or moving parts. You want to respect the machine, know where your body is. You know, a lot of people don't have a lot of experience on these tools, and you need to think about how you approach these tools and use them and your body positioning. So I kind of like to use the analogy of the way that you address your anvil. You know, you want to have a good distance from your anvil to where you're standing comfortably, and both your feet are flat on the ground, and you're not leaning or not too close. And you don't want to apply excessive pressure to where if you slip, you know, you could move into the belt or something like that. So just you know, be careful when you start incorporating tooling into your shop. This could be, you know, power hammers or anything. You know, learn the safety protocols for those things and be careful. So for grinding positions, my grinding videos in here are pretty brief, but I don't have the guards and the rest on because the pictures and everything have a little bit, you know, more clarity. There's less going on in the video. But with this tool, you want to get an angle onto the business end to where you're going to get a slope. I like to grind in an up position because then I can see if my if my business end is square. So am I putting 90-degree corners on there, or am I starting to go sort of rhombus, just like with forging? I can also see the size, so I can see if I'm going to grind too far. I should mention that this is the same tool essentially as the one that Victoria just demonstrated. The business end is the same size and same radius, so it matches up to the other tool. And to get that, you're going to add an extra 1/8 of an inch of thickness. So where hers was to an end that was 5/16 by 3/4, this is 7/16 by 3/4. Okay, now I just usually square up the ends. I'm going to get my bevel on here. When I'm satisfied with that, I'll take my corners off, just like I'm making a round end. So you take the corners off, and then the corners off of the corners, and then you round everything up. And now I want to hit my corners, and I want to basically have little sort of ball ends on the corners here. And I'll match that up with the bob punch, the little round ball fuller that we're going to be doing, so that those match each other. So that when you're making your eye, you can use where this one ends at the corner of the nose there. You can set that little bob punch in there, and you can clean up with the bob punch for adding detail up in the eye, right up in here. Okay, you're going to have a side set, and there's a lot of these. I'm just going to try to go to some of the specifics of the sizing with these. This is going to be after you're going to cut in with your hot cut here to isolate stock, to have a definition between the gums, the gums and the lips, and then the teeth right here. After you've got the cut there, then you've got a little impression to set this tool into, and it's really for pushing the material. It's not a sharp edge there. It's to stand everything up and add definition. So there's a little bit of a glare. You can actually see the edge comes over to about here. So it's about 85 degrees. This is very, very close to 90. You're going to do, for this one, you're going to do a 1/4 inch taper at the end. It's just a square taper. And then after you've forged that square, then you'll file or grind to 85 degrees about. It's, blacksmith 85 degrees. Okay, so we'll just do a quick tapering video here. You're going to use the round side of the hammer, turning 90 degrees between hammer blows. You'll notice I rolled it 180 degrees at one point to do even forging. And then after you use the round side with the horn, then you're going to come to the face and clean up all the edges and chamfer your corners. And again, notice that, I'm working with some heat. Now it looks like it's getting a little cold here. And in my shop, Victoria and I had some really bright LED lights to pick all this stuff. So all my videos look like the color range of my stock is actually darker than it really is in actual fact. So bear that in mind. If you were in a shop that you didn't have a lot of, hot glare coming off of bright lights, and you were getting into those ranges, then I wouldn't be forging those low. But in my shop, it actually appears to me a little bit brighter in color. And then this one is super easy. You're just tilting to about an 85 degree angle, try to keep everything square, and press in until you've got the angle established. This tool here, you want to just take the sharp off of it because you don't want it to cut. You want it to be pushing around. So after you've done that, then you can use a file and maybe a little bit of sandpaper to clean that up. Now we're getting into detail punches. These are all the ones that are going to have round tapers. We have an ear punch, which is going to be 3/8 of an inch at the end, 3/8 of an inch around. You have this bob punch, or you might know this as a ball fuller. That's a 1/4 of an inch around at the end. And then you have this one, the eye punch. You have to make this bob punch to make the eye punch. This is 5/16 because you have to have a good footing for this punch to fit into. Then you'll grind or file down. This one here will be 3/8 of an inch at the end. And then this edge here will be 3/8 of an inch long. So this finished diameter here is about half. But what I'm looking for is after starting at 3/8 of an inch diameter around, I have this 3/8 inch long edge on the business end. So you're going to do square, octagon, round. Use good forging principles. It's especially important when you're using tool steel to use good forging principles, because the types of stresses that you'll get in mild steel will be amplified when you use tool steels because of the addition of the other elements in steel. So you'll show any flaws in your forging when you do it with tool steel. So this will be for the ear punch. It's kind of like a center punch. And we're going to take this from square to octagon to round. I'm going to take the corners off of the corners. And then after that, I'll take another heat, and then I'm going to roll this. Now you could work on, just rounding the end. On my tools, I like to work up into the stock, but you'll notice that marks are an octagon. A lot of that's just really aesthetic preference. So, make this tool your own. What matters is that you have 3/8 of an inch round at the end. So this is basically a recap, but this is good to see where this is used. This is going to punch into the ear. And I would say, I don't know, maybe this is like a 45 degree angle ish. So with the ear punch, again, I see a lot of people, they'll grind their center punch points, you know, off to the side, so perpendicular to rather than the platen rather than up and down. But again, I like to see when my point is meeting in the middle, which I can see when it's above and it's in my view. And I like to start with a short taper, and then just like with a taper when you're forging, you do a short taper and then you extend that back. So I did a little bit of a short taper, and then I continued to grind, turning as I went until I got my 3/8 of an inch. The bob punch, and this is where I was saying it kind of matches up to the sort of ball end corner on the fuller. You can see it can be used in there to define the eye where it meets the ridge of the nose. You're going to take that to a 1/4 of an inch round and file the end so that it has no sharp edges, essentially a ball. And this is a real good tool to use that shoe shine deal that Victoria showed you. So we're going to be squaring the end up a little bit. Now my hands are out of position because I was trying not to work around. So you'll see right here, I'm a little awkward how I'm filing because I'm trying to file backwards and stay out of the view of the camera. But essentially what you do is you approach this like you would a square octagon round taper as well. You'll do a bevel all the way around, and when that bevel is about the size of the flat little spot you have on the end, then you take the corners off of the corners and the corners off of those corners, and then finishing with sandpaper really helps with that. Especially when you can wrap that sandpaper around the edges, it'll take out any hard edges. And that's pretty important when you're doing something like that, because all those hard edges can show. Now, sometimes that's texture, and it really depends on what you like to see in your work. Eye punch. You're going to do a round taper to 3/8 of an inch. Now, you'll recall I said it's going to finish at 5/16 before you do your bob punch on the end. But you're going to help yourself out by getting a little bit of a cup here. So you're basically doing a controlled application of fish lipping. It's what you're always trying not to do, and now you're going to try to like really emphasize all the things you normally try not to do to try to encourage that. So Darryl calls this a slithering blow. You have to do it very lightly, because if you do a penetrating blow, then you'll still forge to the center of the stock and you won't get this cupping. So light blows will cause fish lipping. So that's one thing. Then this sort of glancing blow that I'm going to show you is going to cause lipping. And then also turning my stock so that I'm forging a round taper, that will cause fish lipping. So hopefully those all combine to get you a cupped end like this. And then you can set the bob punch into that cupped end and clean the concave inner surface up using the bob punch. So you can see I'm doing a glancing blow that's coming off this way towards the off edge of the anvil, and I'm striking lightly and turning as I go. All of those things encourage cupping. I use this same principle when I'm doing cupping tools on large tools for making hammers. Once I've gotten that cupping where I want it, then I'll do this. I'll clean this end up to the 5/16, and I'm continuing to turn it because I want to emphasize that that cup. Now I'm going to take the bob punch that we just made. The bottom end's resting on the box of my vise. And now I'm going to turn it so that I equalize any irregularities, and then I'm going to steer it and aim it at any areas of this punch that I want to try to target. So this got a little out of whack, and then I had to do a little bit of straightening before I did filing. Now, you can do these two different ways. On my tools, I like to have a little bit of a sharp edge on the rim, which helps you get a little bit of a bite, but that adds kind of a hard look to your forging. So looking at Mark's, this is a little bit more rounded on the edge, and I think that's gonna just that's gonna lend a little bit to your aesthetic preference. And again, this is gonna be your bare head. So if you want more texture or whatever, make it the way that you want it. But basically, you're going to now file the excess off, leave a little rim. You can soften that up and round that up and leave the rim, or like I did, I put a little bevel on mine and that helps it bite just a little bit. For mine, sometimes I have to push my eye up from a mass and then kind of move it around, and it really helps if you can grab on by getting a little bit of a bite, but then you'll get some sharper edges too, sharper lines on there. Okay, so I'm just going to clean up the end a little bit where I had some excess thickness, and then I'm going to file until I've gotten that little rim. So it does have a little bit of a flat spot left. Then I'm going to turn it, and I'm going to keep on filing all the way around until I've gotten the thickness that I've decided I want for that to be proportionate to the work that you're going to do. And that is, just a fair amount of filing. Okay, so you have these fullering swages. Darryl calls them fullering swages. I talked to Mark about this, and concave fuller is another way you might think about this. This is just kind of like the exact same profile that you use for forging like pipe for bamboo in guillotine tools, that sort of thing. So it really is a fuller. You'll see it's a little flat on the end, so you can use it for planishing, but the edges are rounded up. I've always called these a fishtail fuller because it just reminds me of a fishtail. So this one's going to be about 1/2 inch wide and 1/8 of an inch thick on the end. This one's going to be maybe around 5/16 of an inch on the end, and about 1/16 of an inch thick. And that's plus or minus. These are kind of general guidelines. They're not hard numbers or targets. Just make your tools match in proportion to each other. The little one is for pushing up on the teeth, these canines here. This one's for fullering the ear from the inside of the ear after you've used your ear punch. So this end right here actually matches that little bit right there, matches the profile of the end of your ear punch. So that's what I mean by saying make them match each other. You're going to start with a narrow fuller or just a flat taper. And you're going to remove material by making a square taper. In other words, you're going to forge the end so that it's a smaller cross section, because steel forges best when it's compact and it has a good relationship, like say a 1-to-1 ratio between its width and thickness would be the same size. And then by the time you get above 3-to-1, if you were to hit these thin edges, you might cause this edge in here to buckle. And that's more important on tool steel too, because if you have buckling in here, you can actually propagate some cracks by forging on real narrow edges. So you want to keep things square until you take it to a flat. So here's this larger fullering swage, and I'm going to work both sides. And I started out maybe, I don't know, 5/16 on the end or something like that, 5/16-ish square on the end. And then by the time I flattened it out, it was the called for 1/8 inch by. And then, you got a smaller tool, then you do a smaller square. So this one was maybe 3/16 of an inch on the end. And then by the time I flattened it, I got it to about the 5/16 by 1/16. And it doesn't need to be really, really exact, but and you could always make this narrower on the end and then just file back a little bit until you've got it to the thickness that you want. So again, that looks a little darker. I'll continue to point that out. I wouldn't hit the stock if it was that color, but it's not a good representation because of the lights. You can use a triangular file. You could use the edge of a square or flat file, or you could use some edge grinding on a belt like I did here. You just got to know that if you're going to use a grinder for small, narrow sections like this, cross sections, it goes away really, really fast. So you're just barely giving a little buzz. Okay, we're getting into chisels now. There are 4. One of them is a flat chisel, and the other ones here are these curved chisels. We'll start with we'll do an overview. The large curved chisels here, you're going to flatten to about 1.25 inches by 1/8 of an inch or so. It's better if it's narrow. Now, the one that I have in the video when I was filing was actually a second chisel, and it's a little big. So I want to point out that this edge, and this is Mark's, is very, very thin. And that's important because when you're cutting into a piece of work and you're doing this sort of figurative modeling or sculpting type approach to blacksmithing, you want these cuts to be as clean of a cut as possible without having, say, if you have a thick edge here, you might do some upsetting, and you'll take the mass that you're trying to work and you're going to scrunch it up and distort the edges. It's one thing that can happen. The other thing is if you got a big cross section, when you cut it, then you've got a big wedge, and then everything's going to peel back. So take a good look at how Mark's is made here. You can see it's very thin. You have the medium one for the tongue and the nose outline. That's this one here. And I should point out, this one is actually 5/8 inch H13. It's not 3/4. You could use 3/4, but it's a lot more work. And H13, by the way, is more red hard than 4140. Red hard is the characteristic that makes it more resistant to deformation while you're forging it because of the chrome and the moly. And then the small one here, you're going to flatten to about, actually, I think it was 3/8 of an inch. But you can see Mark's is done on the diamond here with he has a much shorter tool than the one that I've demoed. I did a flat taper and then I ran it into a swage. You can see that Mark did more of a diamond taper. And if I was to do this, I would get a little bit of a tool impression in here that was a little undersized, and I would come back through with like a rat tail file. This one right here is going to be 5/8 inch wide, and I used a 3/8 inch top fuller for that one. Okay, the curved and the curved chisel and the large flat chisel, those are all the same proportions when you start out. 1 1/4 wide by 1/8 thick. It'll put a little rounded cross section on the end, which you're going to cut with a hot cut, and then you're going to curve and file. You can see the indexing here is what we're pointing out. Here's the indexing. So it's I actually have this turned the wrong way, but you're going to have it parallel with the indexing. Works best. So you're going to angle slightly. You're going to forge both sides evenly. You can see the end is a little bit curved here. That's what we're going to remove with a hot cut. You're going to continue to work your flat plane back until it terminates at the same spot that your indexing terminates. You're going to go square to the center axis of the tool and trim with a hot cut just to make things faster. And then if you want to visually reference whether or not you've got a good even forging, this line here is going to tell you whether or not you forged this evenly. For instance, if you had a big hollowed concave section in there, that would be an area that you haven't hit enough. And as you hit it, it will fill out. If you have a bulged area, that's an area that you've hit more, and you want to avoid that until you've worked the adjacent areas. Once you've done that, you want to make sure that you're maintaining this same geometry. So don't elevate your hand when you're working the edges. You want to make sure that the stock is always flat on the face of the anvil. And here's another, this is an example of what I was saying. You want to terminate your bevel up where the termination of the indexing is. So you'll have this sort of peaked belly in here. Then you're going to, when you hot cut, anytime you hot cut, you never want to cut all the way through. These things go ballistic really quickly and they fly to unpredictable areas. So that's my biggest concern. Secondary concern is I don't want to damage my tools. So you want to cut to where you've left a little bit of a buffer, you've got a little bit of a chad, then you go off the off edge and use your hot cut a little bit like a shear and trim off edge. And you're going to clean up in the vise with a file. This particular chisel has a V bevel on it, but you can do a chisel grind, meaning a bevel on only one side. Depends on what you're going for. Sometimes I'll do that if I want to, you know, have a more clean cut on one side and then for it to peel up on the other. Not in this case, but just know that that's an option. This edge is sharp, and as shown in Mark's book, I would anticipate that this is rounded on that side, so that if you're working on a split, you can work your split open. The curve chisel. So the curve is done in a 1.5 inch round, half round swage. It's the same one that we use as a bolster for the leafing hammer. So that's good to know. Curve the back. You curve it back at least 2 to 3 inches. That's from this and up into the tool. You're gonna move the tool side to side in the swage to be able to target it so that you get an even curvature, and then file to finish with a half round. Here's the forging process for this. We're gonna forge that flat chamber. You can see at a slight elevation. It doesn't have to be a real big portion. You can see there's a little hollow there. That area needs more work, and you can see it as I hit through there. Fast forward, we've got a cut started on the face. I'm going to cut off the edge of the anvil and a little bit off screen too, so that's cool. And then trim that off. Now we've gone over to a swage block with a 1.5 inch round. You could have a hardy tool for this. I'm using my leafing hammer because it allowed me to work where I wasn't going to interfere with my knuckles over here. You can see my knuckles are, you know. That leafing hammer worked out really nicely because it has a long peen and it allowed me to get in here. But I usually will use my cross peen in a swage in my handle. I just have and if you do the curriculum, then you're likely to have a leafing hammer too, so that's cool. Okay, so then you're going to take that and then you're going to file. This side is going to be your flat edge, and the back is going to be a bevel. This is a second tool that I used for this filing video, and it's thicker than I would make, but just bear that in mind when you watch the video, that you would want to forge thinner than this. Okay, so I've got a bevel started here on the back, but I'm going to take this bit out here is what I want to show you, because that is going to create a lot of resistance on the cut, and you want this to be able to cut back pretty far. So I'm going to take all of that out to where it's not going to do a lot of upsetting and act like a big wedge either. So this is where it's used. It's used for the mouth with the curve down. You're going to file your edges, then you're going to heat treat all of these, exception of the one that we'll be getting to shortly. They're all 4140 and will be heat treated the way Victoria described. The medium and small curve chisels. We're going to, this one here, the medium is the H13, and this is Mark's, which is a little different than mine. I did a flat chisel like this. You're going to use a narrow fuller and a wedge, just like I just showed, but it's going to be some smaller fuller. And here's the H13 one that I did. I think I had it 5/8 of an inch wide, if I remember correctly, and then I had about a 5/8 of an inch swage, and then I tapped it on the edges, which was able to tighten that up a little bit. So you're going to forge it real thin. The whole reason why you're going to do H13 is you want it to be very thin and still hold up. And H13 is a hot work steel. That's what H stands for, is hot work category of steel. And so you're going to forge it to 1/16 of an inch, and then about 5/8 wide. I might have moved up to a half inch. You know, just you can try the larger one. If it's not a tight enough curvature, then you can just go to the next one, or you can work on the side like I did. And then you're going to finish with a grinder in this case, because H13 hardens in air. So if you let this come down to room temperature where you can handle it, your file is going to skate off of that. You're going to have no luck with that. If you have to file it because you don't have a grinder, then you're going to have to do that hot. In general, I try not to file hot because the teeth are fine. So the rule of thumb with files versus rasps is that rasps, if you rasp cold, then you pop the teeth off of your rasp. So you want to save your rasp and have it last longer. You rasp hot. Files, on the other hand, tend to wear the teeth down and clog the teeth really bad on hot materials. So you want to file cold in most instances. This would be an exception where I wouldn't do that. So here is the piece already drawn out, and then I'm going to come through here and swage it. Now you'll notice it looks like it's kind of cold, but again, we have the real bright LEDs. This tool in particular, I want to stress that you cannot work it cold. So it looks cold in the video. It's on the very lower end of where you would want to even do it. And in fact, I would recommend you don't work it as cold as I do. I have a lot of experience with H13. There's still some color in there. You can see there's a little bit of a dark rose color. But I came back for another heat and I'm working this back a little further. Now at the end of this particular part of the video, you'll see that I'm turning it on its edge, and you can see that it's still got hot heat in it because of how easily you can see that material move. Now H13 gets hard really quickly, so there is actually a little bit of heat in here, but there's not a lot. So just bear that in mind. The problem with H13 is it's an air hardening steel. So not only do you have the problem of the blue brittle range, but when you get it down to around that blue brittle range with H13, that's the range that it's starting to form martensite. So one big problem with H13 that people do is they forge it too cold, and then that will set up stresses that will result in cracking and tool failure later. So now we're going to kind of do a little bit of an overview. We got to heat treat this, and I've been talking about that. So we're going to do an overview about heat treatment in general. So let's just talk about what we know about heat treatment. So iron is a solid solution. I put this in parentheses so that, for emphasis. And just like quick review of what that means. A solution is a mixture of two or more elements comprised of your solvent and your solute. So an example would be salt and water, and your water being your solvent. That's what the salt, which is the solute, mixes into, and salt water being the solution, right? Steel is iron with carbon. Iron is the solvent and carbon is the solute. So the carbon can dissolve into the iron, right? So that's why we're calling it a solution. Why does steel harden? Okay, steel hardens because, as Victoria mentioned earlier, in a normal state, let's just back up to what you would call like baseline state with steel. If you just let it cool gradually, it's going to form what's called perlite, and that's soft. That's what's happening when you normalize something. When you anneal something, you bring it up to temperature, you let it cool down slowly, and it's soft and stress-free. It has carbon in there, but it's not distributed really evenly. Mostly you have the ferrite, that's the soft stuff, and then you got this other stuff called cementite, and mostly carbon's tied up in that cementite. So the structure of iron is this cubic lattice. You probably saw that on the chart that Victoria put up, and there's these couple of little cubes on there. They look like a six-sided playing die, like you play dice with. So that's how carbon molecules arrange themselves. They arrange themselves on the lattice. And when I say molecules, I mean the atoms themselves, so the atoms of carbon. And iron and carbon can rearrange themselves on this lattice, right? So as it goes up into critical temperature, that lattice changes a little bit, and then depending on how fast you cool that, the carbon is either going to stay on that lattice or it's not. And what we want it to do is we want it to stay on the lattice. So I want to have a couple of visual aids so you can visualize this. If you want to know more about this, and I recommend that you do, you're not going to get everything that you need to fully understand this subject, in a single talk. And, there's a lot of terminology that you need to learn and some concepts. So I found a good site called msestudent.com. That's material science and engineering student.com. And it explains a lot of these really well. But I want to point out these little cubes because this is important. This is what's going on internally when you get this up to austenite. All steel, regardless of carbon, will do this. at room temperature, or when it's cooled slowly, it has an atom in the middle. And then when you heat it up to that critical temperature or that transformation range, you get thermal expansion, and all of a sudden some other iron atoms pack on. These are all iron atoms, right? And that's not really necessarily what's important. What's important is that carbon can pack on too while those extra iron atoms are packed on. So that's called a phase change. And at low temperatures, perlite is formed, and the carbon is less soluble in what's called alpha iron. That's the iron that's at room temperature, or is allowed to cool slowly. That's what happens when you normalize it. Anything below critical temperature, and it precipitates out and forms this thing called cementite. I know this is getting a little bit ahead, and a lot of this is just this is kind of like my math, right? Not everybody's a math person, but if you kind of want to fully understand this, it helps if you kind of at least get introduced to this a little bit. So all the carbon is in this cementite here, and it just looks kind of like cement under a microscope. That's why they named it that. At higher temperatures, you form austenite. The carbon becomes more soluble. So it's exactly what's happening if you have a glass of water and you heat the water up, then salt will dissolve more readily into the water. Well, you've changed the solubility of your water. And at higher temperatures, the solubility of carbon and iron changes, and carbon can diffuse out of the cementite, and it can go into the other parts of the steel. And you'll imagine that it probably takes a little bit of time for it to move from one place to another. And that's why you want to do your soak, because it takes a little bit of time for that carbon to diffuse. So getting back to that little cube lattice, this is your ferrite here. This is when you don't have any carbon attached at all. And these little gray guys, that's your carbon. You'll see that those are able to stick in here on these edges. So austenite, what's important about going from this structure, this body centered, where there's one atom in the middle, to this structure here, is the spaces get a little bit bigger or more available for this carbon. There's more places, and the carbon will start attaching and forming austenite. So it's going into solution, just like salt and water go into solution when you heat it up, or more readily. And then when you freeze it, it gets stuck. It goes back to this, but it gets stuck with these carbon guys on there. So that's the whole point of what you're trying to do, is you're trying to bring it up to where you have austenite, and that's basically making these sites available for the carbon to stick. And then you freeze it by cooling it down too rapidly for that carbon to go somewhere else. Normalizing and annealing is when you cool too slowly to make martensite. This is the hard stuff that you get from austenite. So normalizing and annealing, they do about the same thing really, but one happens over a longer period of time. This is if you insulate with like vermiculite or ash. So anyway, they're both forming perlite. And hardening has two components to it. You've got to heat it up to within the specific range. That's the critical temperature or transformation temperature where it makes austenite. And then you need to, there's a cooling factor to this. You need to cool that fast enough that it doesn't form this stuff, the perlite, and you want it to make the martensite. So tempering, what does tempering do? Tempering degrades this martensite that you made, this real hard stuff. It starts to break it down, and it actually starts turning back into perlite. But the cool thing about being able to temper is that when you're applying heat, you're applying it in a controlled way. You can apply more heat or less. And if you apply less heat, then you form less perlite. And if you form more heat, you'll form more perlite until all the martensite will go away eventually. If you temper too much, then you take all your hardness off, and you'll know that because you know not to, say, heat up the end of a chisel when you're grinding it on the grinder, or else it'll go soft. That's because you've broken down that martensite. So the cool thing about tempering is that you could take the same piece of steel, and that piece of steel could make a chisel that'll hold a real fine edge over a long period of time, but you're not going to try to pry open a paint can with it because you might snap it. On the other hand, the same piece of steel you could take almost all that hardness off, and you can make a spring, and you can put it on a truck and put a bunch of weight in the back and bounce it up and down the road for hundreds of thousands of miles, and it'll stay tough. So tempering is what allows you to do that, and that is by having a controlled drawback of how much martensite there is. This blue range here is going to be where you form perlite, and let me explain what we're looking at here. We have time here on the bottom in seconds, so this is in 1, 10, 100 seconds, and this is temperature. Unfortunately, it was Celsius. Up here, this would be your critical temperature, and these arced lines here, these are what are called cooling curves. Now you'll notice that this blue is specifically where perlite forms, and you'll notice you're coming down over time. Now this one right here, you'll see you come down over time and it misses the blue. It's ahead of the blue, and you'll see that if you're ahead of the blue in this area, you're going to form martensite. These lines, on the other hand, you can see they go through that blue. So this is coming down over, this was 10 seconds, and this would be representative of how fast water cools, okay? Right here, this is your normalizing. You'll notice it's 10 to the second. So that's 100 seconds. That's normalizing, okay? And then you'll notice over here, 10 to the 4, that's a lot of seconds. We don't need to worry about how many, but that's going to be annealing. That's if you insulate. There's a reason why I'm showing you this particular chart. This is called a time temperature transformation chart, a TTT chart. It's actually TCT because it's got the blue outline. But the point is, you've got to miss this it's called the nose. So this is when perlite forms, and you can see it forms over time. So the whole point is to sort of race past that, and that's going to get you your martensite. I'm going to tie this in with air hardening steels here in a second. People always ask the question, well, how does an air hardening steel harden in air? The reason is because this area that forms perlite is over here somewhere. It occurs later. So it still will occur, but it just occurs later. So you have a bigger window here. Instead of being 10 seconds that you need to race past the nose, it might be 100 seconds, or it might be 500 seconds. Who knows? It's every steel is different. So you got to get the chart. It's called a data sheet for each steel. So let's take some of those things, and what do you need to know? This is a generic chart. So you've got time and temp, and you can see there's no values on here. And what you need to know is that austenite forms within a range. There's a lower transformation temperature and an upper. It forms in proportion to how high it is in the temperature. If you're down here, you will not have as much of your carbon go into solution as if you're up here. So you want to be up here without exceeding that. And then you have martensite down here. That's pretty well fixed. It's between 600 and 400 degrees. Okay, and this green this green here is your cooling curve. So you need to come from austenite down to martensite, and you'll notice it's not a straight line. That's because usually you don't have a straight line from point A to point B. It usually has a little bit of an insulation because of the vapor jacket you're trying to break up, and down here it gets into what's called convection cooling, so it slows down. But imagine the whole idea is that you need to get to here from here to here in an appropriate amount of time. So imagine that you're in a room, and on the far side of the room there's a door, and you need to get through that door, but the door is closing. So you just need to get there before the door closed. A steel like water would be like a steel that the door is closing fast. So you got to run, because you got to get there in a short amount of time. So you got to run to get through that door. Now, you don't necessarily want to keep running and hit the wall on the other side. You don't want to crash through the door, but you do need to hurry. Now, if you had an oil cooling steel, something a little longer, you might be able to walk before that door closes. In air, you might be able to stop and have a cup of coffee and have a chat. But the point is, there's an appropriate amount of time, and the key is just get through the door. And this top line on martensite is what you need to get to, from there to there in an appropriate amount of time. So why does this actually matter? Because I know I'm repeating some of what Victoria said, but it matters because air is actually quench, because it's pulling heat off of your stock. So it's not normalizing your steel because it has other additions of other alloying elements. It has a higher proportion of chromium and molybdenum, has vanadium, and that sort of stretches out that whole window, so you've got a larger window. All the rules still apply. You can still form perlite with air hardening steels. You can still anneal it, for instance. But to anneal it, you've got to have the annealing process go over a 24-hour period in an electric kiln where it's coming down, 15 degrees or such and such degrees over every 15 minutes. So you can't do that in a shop setting. And that's really important, because if you're not understanding what's going on, you could make an unsafe tool. You could still have hardness on the struck end. So what that means is, now that we've kind of talked about what's going on, if you heat past critical temperature on an air hardening steel, and air is your quench, then you know that if you get this hot enough, then it will quench. So you can't normalize this or anneal this in a practical way in the shop. And just to emphasize that, like I said, you can get a data sheet on all of these tools, on all steels. Right, this is right from a tool steel manufacturer. Bringing this up to critical temperature, look at this range, 1800 to 1890. Well, first thing that you need to notice is that that's a lot higher than what was shown on that earlier chart. That's really, really hot. You can do as low as 1800. It says air is the quench, meaning air is sufficiently, and this is why that chart, getting back to what Victoria said, sufficiently rapidly is the wording, because there's different rates of cooling that you need for different categories. And tempering, this is another thing that I want to point out, is that technically you should be tempering at 1000 to 1150 and hold for an hour per inch. Well, you're not going to do that in the oven that you bake cookies in, right? Hardening H13 without a kiln. Now I have a kiln, so I can anneal this. So I have a struck end because I can do that, but you don't want to ever heat this whole area up, okay? And what are the particulars here on here? It's gonna harden in air, and you need to heat it to 1800. So how do you know what 1800 is? The best way that I would recommend if you're going to start working with steels like this is, as Victoria said, you want to start with your magnet and know that that's at 1420, and then learn your heat treatment range for normal steel. And you're going to start having to learn how to gauge by color, but everybody perceives color a little bit differently. So you're going to have to figure out how you see the color. To me, I perceive the color as sort of a bright orange, but if you look at the chart, it's not really in an orange range on that chart. Or maybe it is. Maybe I don't perceive color that way. So you can start to ramp it up, but you'll know that it's hardening with H13 if the scale starts to pop off. So scale popping off is a good indication that you're forming martensite. And you always want to have safety glasses when you're working with this steel, because this stuff will fly. But if you don't bring it up to critical temperature and it doesn't have the scale pop off, remember the color that you did, and don't take it all the way up to what you think is 1800 and then just, try to guess at it. Get it a little bit hotter, like a shade hotter than what you would do normal steel, and then let it air harden. If you see that scale pop off, test it with a file, see if it's hard. And then if it's not, put it back in the forge. It won't hurt it. Bring it up another shade past that. Leave it. Now, I wouldn't leave it. I left it on this vise for the picture, but the way I do it is I hold it in my tongs until the scale pops off. And I go through the process of what I would normally do with a quench. And I hold it in the tongs in regular air. And when I get the scale popping off, then I know that it's hardening. So to do this all, to spec, you would need one of these guys. You need an electric heat treat kiln. And that's not to say that you can't work with H13 in a shop setting. You just need to know how some of these rules apply so that you can do it in a shop setting. So one thing is, you can temper at in a regular oven between 450 and 475, and do that for a long period of time, 2 to 3 hours. And then that's going to be your initial tempering. And then if you recall, the tempering that it said was 1150 degrees, 1000 to 1150. Well, you can do either a hotter temperature or you can do a longer time. Both will continue to break some of that martensite down into perlite, which is going to get you your safety factor. So if you leave it longer, then it gives it a longer period of time for it to break down a little bit and add some safety to the tool. So you do a longer period of time. Remember, you can't normalize it, so don't get your struck end hot in the first place. However, me, just because I want to be extra safe, I'll always use a plumber's torch. And even though I don't get the ends, the struck end hot in most cases, I'll still temper because I don't know if I maybe had some heat transfer and I just want to be extra safe. Now, you'll remember from the tempering diagram there, it had all the examples of color. Once you get through the blue range and it just starts to go to a gunmetal color, that's 730 degrees. So if you take it up to about that temperature where the blue goes out and it goes to a metal color, a gunmetal color, that's 730. And if you do that a few times, then that's approaching pretty close to 1100. And that's a pretty safe bet to make sure that you're safe. If all of this is too worrisome, if this is too much, then, just use the 4140. That's fine. But if you want to start getting into air hardening steels, just understand that everything you know about heat treatment still applies with air hardening steels. And you just need to understand how to make that tool safe by using air hardening steels. You thought we were done, but there's still one more. Okay, so we've got this corner bend chisel. It's a taper on the end with a bend in it, and the taper is to about a quarter of an inch. You're going to bend it. You can upset into the corner, or you could do a Haberman corner where you use a peen and you draw this corner out and it's going to fill into the corner. Mark did a Haberman corner. I did an upset. I did mine before I talked to Mark. And then you're going to, draw that out. So you're going to do a little tiny upset, take it to a quarter of an inch on the end, keep a little bit of an open angle from 90 if you're going to upset, or for that matter, just do a Haberman corner. It's your preference, whatever you're more comfortable with. And then clean it up and get it to 90 degrees. And then mine ended up getting a little short, so I had to draw it out a little bit, but then you're going to take it to a little bit of an edge chisel profile. And this is for grooving the tongue. And this has to fit down into the mouth. So here we go. I'm taking it on the off edge, bringing it just above 90 or open from 90, maybe 100 degrees, a little upset, and then cleaning up my corner. Went a little too far, but I have the means to fix that. So I use my hammer like before. Figure that out. And from there, get up a little, then you're going to bring it down to the thickness that you need. It's a pretty thin edge. And then bevel it. I wanted my edge to be straight, so I just clean it up. And then I ground a little bit of that back so that it can fit into the mouth, and then cleaned up my edges, and then at the end put an actual little edge on here. And that is it for me.